Everyone, my name is Nahush Bhamre, and today I will present our research titled Enhancing Naive Bayes Algorithm with Stable Distributions for Classification. So this research was carried out in collaboration with Ms. Pranjal Ekhande and Professor Eugene Pinsky at Boston University. So here is an outline of the presentation. We begin with an overview of the Gaussian Naive Bayes model, discuss its limitations, and introduce stable distributions as a more flexible alternative. We then described our proposed stable naive-Bayes model, outline its methodology, and review the experimental results. Finally, we conclude with implications and potential directions for future research. So let us start with the Gaussian naive-Bayes model. So the naive-Bayes is a family of probabilistic classifiers that apply the Bayes theorem with a strong assumption of feature independence given the class. Despite its simplicity, it performs surprisingly well in many domains, especially the ones which have high dimensional data. One of the most used variants is the Gaussian naive Bayes, sorry, which is a parametric model that assumes the features allow a normal distribution within each class. The Gaussian naive Bayes is widely applied due to its closed form solutions for likelihoods, making it computationally very efficient and very easy to interpret. It has been particularly effective in text classification, medical diagnostics, and real-time applications where speed is essential. But the Gaussian naive Bayes has its own limitations. It performs poorly when the data deviates from the Gaussian assumption, such as in the presence of skewed distributions or outliers. And these violations distort the estimated likelihoods, and which lead to suboptimal classification results. So talking more about the Bayes framework itself. So to classify a new observation in the Gaussian naive Bayes, we use the Bayes theorem. The posterior probability of a class given the features is calculated as the likelihood of the features under the class multiplied by the prior of the class itself and divided by the overall evidence. The key part here is the likelihood. Under the naive Bayes assumption, we treat each feature as independent, so the likelihood becomes a product of the individual feature probabilities. And since this is Gaussian naive Bayes, we assume each of these features follow a normal distribution. That means we use the Gaussian probability density function to compute how likely each feature value is given the class. In practice, we calculate this likelihood for all classes, multiply it by the prior of that class, and choose one with the highest posterior probability as the final predicted class. The Gaussian distribution itself, it is more commonly known as the normal distribution. It is one of the most fundamental and widely used distributions in statistics and machine learning. It is characterized by its iconic bell-shaped curve, which is perfectly symmetric around the mean. The distribution is fully defined by just two parameters: the mean, which indicates the central tendency, and the variance, which controls the spread of the data, the dispersion of the data. One of the key assumptions of the Gaussian distribution is that most data points lie close to the mean and that the likelihood of extreme values falls off rapidly. So in other words, it has light tails, making it well suited for the data that does not contain outliers or significant deviations from mean. The strengths of the Gaussian distribution lie in its mathematical simplicity and the fact that many natural phenomena approximate a normal distribution under the central limit theorem. Its well-established statistical properties make it very tractable for inference and modeling, which is why it is the default assumption in many classical machine learning algorithms, such as this very the Gaussian naive Bayes or the linear discriminant analysis. And it is currently being used for some activation functions or other things in the neural networks as well. However, this same simplicity becomes a limitation in the presence of real-world complexity. The Gaussian distribution cannot adequately capture skewed data, where the distribution leans to either left or right side, or maybe heavy tail data, where extreme values occur more frequently than we would normally predict. And in such cases, relying on the Gaussian assumption can lead to significant errors in probability estimation. And this is one of the motivations for exploring more flexible distributions, such as the stable distribution, which can better model these deviations from normality. The stable distributions are an important generalization of the Gaussian distribution. Unlike the Gaussian, which assumes symmetry and light tails, stable distributions are capable of modeling both skewness and heavy tail behavior. This makes them particularly useful for describing real-world data that often contains outliers or extreme values, for example, in finance or environmental systems and signal processing. So what makes stable distribution unique is their parameterization. They are defined by not two parameters like the Gaussian, but four. First is the alpha, which ranges from 0 to 2. It is known as the characteristic exponent and determines how heavy the tails of the distribution are. A lower alpha means fatter tails, which implies a higher likelihood of extreme observations. The second is the beta parameter, which controls the skewness and ranges between -1 and 1. It allows the distribution to be asymmetric. It's shifting its weight to the left or right side. Gamma is the scale parameter and influences the spread of the distribution, similar to the standard deviation in the Gaussian case. And finally, delta, that is the location parameter, which determines the central point of the distribution. So these four parameter structure gives stable distribution a higher degree of flexibility, allowing them to represent a wide variety of shapes and behavior beyond what Gaussian models can capture. So stable distributions offer several key advantages as we discussed. The first is flexibility. While the Gaussian distribution is restricted to symmetric and light-tailed, stable distributions can expand the modeling space by allowing for both asymmetry and heavier tails. This enables a more accurate representation of the data that deviates from the idealized normal case. In terms of robustness, stable distributions are more resilient to outliers and extreme observations. This makes them better suited for real-world applications where data is often messy or contaminated by rare but impactful values. In such cases, models built on the Gaussian assumption may fail to generalize, whereas stable-based models can maintain performance. Finally, stable distributions are backed by the generalized central limit theorem, which extends the classical result to cases where the data generating process involves heavy tail variables. This makes stable distributions theoretically appropriate for modeling sums of dependent or non-Gaussian variables, which is especially relevant in domains like finance and environment modeling. So this slide illustrates the fundamental difference between Gaussian and the stable distribution and highlights how stable distribution adapt their shape based on the alpha parameter also. So on the left side, we see a direct comparison between a standard Gaussian distribution and a stable distribution with alpha equal to 2. Since alpha equals 2 corresponds to the Gaussian case in the stable distribution family, we can see that the two curves are nearly identical. This demonstrates that the Gaussian is a special case within the broader family of stable distributions. However, we can also notice that even with alpha set to 2, subtle differences in the tails or scaling can emerge, depending on how the parameters have been estimated. And on the right hand side, we observe the stable distributions plotted for different value of alpha. As alpha decreases from 2, the shape of the distribution changes dramatically. Specifically, the peak becomes sharper and the tails become heavier. In other words, the probability of observing extreme values increases as alpha decreases. This feature is crucial when modeling real-world data that contains outliers or heavy tail behavior that Gaussian distributions cannot capture. So together, these two plots emphasize the flexibility of stable distributions. They allow us to smoothly transition from light-tailed symmetric behavior, which we observe in the Gaussian, to highly peaked, heavy-tailed distributions by simply adjusting alpha parameter, a single parameter. This is what makes stable distribution particularly powerful in scenarios where the Gaussian might fail. And in this slide, we introduce the core concept behind the stable Naive Bayes model. At a high level, sorry, the stable Naive Bayes preserves the structure of the classical Naive Bayes classifier, but replaces the Gaussian assumption with a stable distribution for modeling the likelihood of each feature. The change is significant because it allows the model to better reflect the nature of real-world data, which is often skewed or heavy-tailed, features that Gaussian-based models cannot represent well. By using the stable distributions, the stable naive Bayes can capture a broader range of distributional behavior, making it more robust in practice. The posterior probability is still calculated using the naive Bayes. However, the key difference again lies in the likelihood. Instead of assuming each feature follows a normal, we now assume that each feature follows a stable distribution. And all the unique parameters alpha, beta, gamma, delta are unique for each feature in each class. The likelihood for a data point belonging to class Ck is given by the product of stable probability density function evaluated at each feature value using the parameter estimated for that class. But since the stable distributions do not have closed form density functions in general, we cannot evaluate these probability density functions analytically. Instead, we rely on numerical approximations to compute the likelihood. This substitution introduces additional computational complexity, but it significantly increases the model's expressive power also. So that makes the stable naive Bayes a more flexible and realistic extension of the naive Bayes framework. So one of the core challenges when working with stable distributions, as I discussed, is that they lack closed form expression for their PDF in the general case. This makes standard analytical approaches to estimating or fitting distributions impractical, and stable distributions must be handled numerically. So to solve this, we'll leverage the stable package developed by JP Nolan in R. So this package includes robust numerical routines to estimate the 4 key parameters based on the empirical data. These parameters allow us to define a stable distribution tailored to each feature in each class. Using this package, we can fit a stable distribution to the training data for every feature individually, assuming independence as in the naive Bayes framework. This allows us to retain interpretability while adapting to more complex data characteristics like the skewness and heavy tails. And the result is a model that is much better aligned with the real world features, especially when the Gaussian assumptions are not valid. To integrate this capability into our machine learning pipeline, we connected R with Python using the RPy2 library. This interface lets us directly call our functions from within our Python scripts, eliminating the need to rewrite or approximate complex estimation routines in Python. The workflow is as follows. We start in Python by extracting feature values by class. Using RPy2, we invoke R's stable.fit function, which returns the estimated stable parameters. These are then passed back into Python and used to compute the likelihoods within the SNB model. This hybrid approach gives us the best of both worlds. We retain R's statistical rigor and precision for parameter estimation while taking advantage of Python's ecosystem for modeling, experimentation, scalability. Importantly, it ensures reproducibility and avoids implementation errors that can arise when manually translating algorithms across the language. So let us now look at the experiments which we performed to evaluate our stable naive Bayes model. So to evaluate the performance, we curated a diverse set of 16 datasets from the UCI machine learning repository. These datasets span a wide range of domains such as healthcare, finance, sensor data, or image recognition data, and which allows us to assess the model under varying distributional characteristics, including skewness, class imbalance, and outlier presence. Reprocessing was a critical step in ensuring consistency across datasets. First, we removed the ID and timestamp column which do not contribute meaningfully to the classification. We retained only continuous valued features as discrete ones are not modeled under the stable distribution. For missing values, we use the median imputation to preserve the central tendency of the data without being affected by outliers. In some data sets, we also replace zero values with a very small constant to stabilize the logarithmic approach, operations during likelihood computation. And to standardize the classification task across all the data set, we converted the labels from the labels to binary using the one versus all approach. The data set was also split into training and testing subsets using a 67 to 30 split to ensure sufficient learning while preserving generalization. And we evaluated performance using two metrics: the classification accuracy, which measures the overall correctness, and second is the area under the curve, or AUC, which is especially useful for imbalanced dataset as it evaluates the model's ability to discriminate between classes regardless of the threshold. To evaluate the robustness of the stable naive Bayes model, we compared it with three other naive Bayes variants. First is the classic Gaussian naive Bayes, which we have been discussing up till now. Second is the beta naive Bayes, and third is the student's t distribution naive Bayes. The motivation behind choosing beta and students t distribution stems from their ability to handle two specific limitations we wanted to handle of the Gaussian model. The beta distribution is particularly useful for capturing skewed data distributions. It is defined on a bounded interval and controlled by two shape parameters, alpha and beta, which makes it highly flexible in modeling skewed or asymmetric data. It was therefore considered a suitable alternative to handle skewness, which Gaussian models cannot represent. On the other hand, the student's t distribution was chosen to address another limitation of Gaussian models, that is their inability to model heavy tails. The t distribution is symmetric like the Gaussian, but has heavier tails, especially for small degrees of freedom. This makes it more robust to outliers and better suited for data sets where extreme values are expected. So by comparing the stable naive Bayes with beta naive Bayes and student t naive Bayes, we could isolate the benefits of modeling both skewness and heavy tail simultaneously. So to evaluate whether the performance improvements observed with the stable naive were statistically significant, we performed a paired t-test across all the datasets. The idea behind this test is to compare the stable naive Bayes against each of the competing models on a per dataset basis. For each dataset, we computed both the accuracy and the AUC for all models. Then for each metric, we calculated the pairwise difference between the stable naive Bayes and the comparator on that dataset. This gave us a distribution of differences across the datasets. So the null hypothesis of the t-test was that the mean of these differences is zero. In other words, that the stable naive Bayes performs no better nor worse or on average than the other models. A low p-value below the standard threshold of 0.05 would allow us to reject that hypothesis and conclude that the stable naive Bayes performance is statistically significantly better. This method allows us to go beyond raw metric comparison and make inference-driven conclusions about performance consistency. It ensures that observed improvements are not just data specific, but also across varied independent settings. So here are the results. Our experimental results show that the stable naive Bayes consistently outperforms both Gaussian and beta naive Bayes. The improvements are not just empirical, they are statistically significant. The p-values are much lesser than the threshold we had set of 0.05. The values are 0.031 for accuracy and 0.017 for AUC. This means the gains are unlikely to be random due to variations in the dataset. When compared to the students' tree distribution, the stable performed comparably in terms of both accuracy and AUC. The differences in performance were not statistically significant. But however, the stable naive Bayes has a key advantage that with the heavy tails, it can model for both the skewness as well, the asymmetry as well. Whereas the t distribution only addresses the heavy tails and assumes symmetry. This makes the stable naive Bayes a more flexible and general purpose classifier. So to conclude, the stable naive Bayes model provides a principled and practical extension of Gaussian naive Bayes. By replacing the Gaussian assumption, With a stable distribution, the stable naive Bayes captures a broader range of data characteristics like symmetry and fatter tails. This results in significantly improved performance across many real-world datasets. However, this flexibility comes with a certain trade-off as well. Estimating stable distribution parameters is computationally more demanding than for Gaussian, particularly because closed form density functions do not exist for stable. Moreover, with 4 parameters per feature per class, the stable naive Bayes introduces the risk of overfitting when applied to smaller datasets. One key aspect of our implementation was that consistent with the naive Bayes assumption of feature independence, we modeled one-dimensional stable distributions for each features. This simplification made the estimation trackable and interpretable. However, for more complex models, especially those that do not assume the feature independence, we would need to fit multivariate stable distributions, which is a much more challenging task, both statistically and computationally. This opens an important direction for future work that is applying stable naive-Bayes style modeling to multimodal data, where features are interdependent and heterogeneous in type. For such cases, the ability to accurately fit and evaluate multidimensional stable distributions become essential. Developing or adapting tools for this and testing their performance in non-naive Bayes framework is a promising next step. So overall, the stable naive Bayes presents a meaningful upgrade to the classical naive Bayes framework, grounded in theory, enhanced by flexibility, and well suited for the complexity of modern data. So thank you for your attention.